Welcome. If you are just tuning in, you missed out on a lesson about hierarchy of dominance. Hierarchy of dominance. Let's talk about a couple of things first. Hierarchy. I asked some students in class, what does hierarchy mean to them? A lot of them came up with kind of these social hierarchies, right? Politics, people in power, and kind of this leveling of classes, let's say, so to speak. And that leveling and that categorization is very much key in the hierarchy of this math that we're going to be talking about today. So think about it as something being more powerful and something as being very weak and not having any power at all. That same kind of thing is going to be happening here. And we're talking about that powerful nature and that dominance, right? How powerful something is. So we're talking about basically that hierarchy, kind of categorizing and leveling things based on their power and their dominance. So something powerful in nature in math is really going to be something that increases much faster. So we kind of can think about these graphically as something that increases very, very fast. It is going to be more powerful and more dominant than something that doesn't increase very fast. So when I say things like dominant, I'm really talking about its nature in terms of how fast it increases. All right, so if you want to think about it that way, let's say a function increases. That might be a good kind of interpretation of this dominance characteristic. Sorry about my writing there. So let's actually talk about the categorization of some of these things. So first we just have to know and be able to identify what exponential functions look like. Now I'm just going to put those terms in there. So we could write like y equals or f of x equals and something like this. Let's write f of x equals. One classic exponential function is e to the x power. Remember that e, even though it looks like a variable, is actually a constant 2.71 something, just like pi, it keeps going on. We could also, not use the exponential function, but use a different base, like maybe a base of 2. These are two different types of exponential functions. Now, obviously, we can add some things on to the back end of that, like +1 or +2, some different transformations, but they're still exponential functions. Polynomial functions, on the other hand, right, look slightly different with how they're built. So something like, I don't know, 4x squared, or maybe just a little bit simpler, x to the third power. These are each polynomials. Now I want to talk about these. Well, each one of those is a monomial put together as polynomials, but we call those polynomial functions. And we can actually notice that there's a big difference here in how these are built. And I want to just kind of stamp that difference in the organization of polynomial and exponential functions. So if I look at exponential functions, we can see that the variable x is the power. Okay, so if we see a variable like x as the power, then it is exponential. And I know that these over here, these polynomials have exponents. That does not mean that they're exponential. Remember that exponential functions increase very, very fast. These might be quadratics or cubics, right? Increase a little bit differently. And when we kind of notice these polynomial functions, we see that the base is the variable is the base. Is the base, right? Or that the power is constant or is a constant. All right, what do I mean by that? Like a regular number. So if you were just to look at the powers of each one of these, the exponentials have an exponent. Sorry, the exponentials have a variable that is the power, whereas the polynomials have a constant 2 or 3, 1, 5, 7, whatever, as the power instead, where that power is not changing. And then of course, logarithmic functions become fairly easy to identify because we see log, but just don't forget that natural log is also an exponential function. I hate the way that came out. Let me try that again. I can do better. Natural log of x will both be exponential functions. Now you're going to have to go into Desmos and you're going to have to categorize things. Like just look at functions and be able to say, this is exponential, this is polynomial, this is a logarithmic function. Now, some things that we should also kind of note here, there's some exceptions like square root of x. Remember, square root of x is actually x to the 1/2 power. So if I need to rewrite square roots as an exponent, then I can see, okay, I have a variable as my base and a power that is constant. That is a constant 1/2, that's not changing. So therefore, that would also be a polynomial function. Now, this is kind of how we classify things. So with hierarchies, we want to know basically where something stands. And then that hierarchy determines how powerful something is based on where they stand. So in this situation, the most powerful are going to be situated to the left here. These exponential functions are the most powerful, and this is organized where these logarithmic functions are the least powerful. And again, that's because these exponential functions increase much, much faster than any polynomial. So any exponential function that you can think of will beat out, well, I should say it has a base greater than 1, will beat out these polynomial functions as long as those exponents are greater than 1, right? And all of those are going to beat these logarithmic functions. So if we can identify them, then we can be able to decide, okay, what is more powerful than the next? Now, there are some tiebreakers here. So for instance, 4 to the x is more dominant. I'm just going to put DOM, than 3 to the x. They're both exponential. So both of these would be more powerful, more dominant than any polynomial function. But 4 to the x is more dominant than 3 to the x because the tiebreaker for exponential functions is the kind of strength of the base. Some people say, well, 4 is bigger than 3. Well, yeah, it is. And it's really just because that's the base of that exponential function. With polynomial functions, we talked about this with limits at infinity yesterday. Something like, I don't know, 2x to the 5th dominates, I should use the same color here, I'm sorry, dominates, I don't know, 5x to the 3rd. And that's because, what's the tiebreaker this time? With polynomial functions, we don't care about coefficients. We're just looking at those exponents. So if they're both polynomial, the tiebreaker is the exponent or the power. Okay, 5 is bigger than 3. With logarithms, we won't really necessarily have to be dealing with tiebreakers and logarithms. So this is kind of how we establish some different things here and what is more powerful. So if I were to think about a couple of different things, like let's just come up with a quick example, 3 to the x versus 5x to the 7th power. First thing I would look for are these exponential or polynomial? And I can see that 3 to the x is exponential and 5x to the 7th is polynomial. So there's no reason to even check tiebreakers. This one, 3 to the x, is always going to dominate based on our characteristics here. Right? Any exponential is going to dominate a polynomial function. And either one of those is going to dominate a logarithmic. Okay, now if I were to change some things, maybe instead of 3 to the x, and I made that, let's make that 4x to the 10th. Which one of those would dominate? Well, they're both polynomial this time because they both have constant exponents. This time, remember, the tiebreaker is the power between polynomials. So I would just kind of highlight those two things, which tells me that x to the 10th would be our dominant term, right? This 4x to the 10th would be the dominant. Just some things to consider. Okay, so now let's actually talk about how we're going to use this to do limits and how we can solve some kind of difficult problems with limits. So let's look at the following. We'll look at 2 different examples here. Let me make sure that I got my notes in front of me. Let's take a look at 2 different examples. Example, let's say, number 1. we'll take the limit as x approaches infinity. Let's do 2 of them. So we'll do, let's say 3 to the x minus 7 over 2x squared plus 5. And then over here, we'll do, I don't know, we'll make that a negative 3x over here. We'll make this 4x squared plus 2x all over 5 plus 2 to the x power. Let's find both of these. All right, sorry, just coming up with examples on the spot. So in this first one, in both of these, we can see that we're finding the limit as x approaches infinity. We're talking about the end behavior of that graph. So we want to know as this function goes all the way to the right, where is it going? So there's a couple different kind of scenarios here. But let's actually just kind of identify, I'm going to say ID, the leading term based on dominance. Okay, what is the most dominant term? So let's take a look. For this first one, we've got leading terms on the top and bottom of negative 3 to the x and 2x to the 5th. Both of those are going to be bigger than constants. So in this case, what we have here are two things that cannot be reduced. Like I can't really divide these to reduce these, subtract my exponents. So what I have to do is I actually have to figure out what is more dominant. All right, so now I'm going to say that this top is more dominant. That is going to dominate the bottom because it's an exponential function over a polynomial. Now, why this is important is because this is going to give us kind of two different scenarios. Scenario one would be if the numerator is dominant. And scenario two is going to be if the denominator is dominant. Now, if they're equally dominant, okay, then we should actually reduce as much as possible and think about what our horizontal asymptote would be, okay? But in these situations, what I want to talk about is specifically if the numerator denominator is more dominant. So the numerator is dominant here. I said that if denom is dominant. If the numerator is dominant, what we're going to do is we're going to plug in a positive or negative value based on the limit that we're trying to take. So since we're talking about x approaching infinity, we're going to put in a positive value, right? Because infinity is a positive number in this case. And we're going to just see what we would get. Negative 3 to some positive number all over, I don't know, 2x to some positive number. Well, let's see what would happen here. We have to do order of operations. 3 to any positive number, like 3 squared, 3 to the 3rd, 3 to the 4th, 3 to the 5th, 3 to the 6th, 3 to the 7th, is always going to be a positive. And then we would take that negative afterwards. So that's automatically going to make it negative. X, let's see, it doesn't really matter what x is here. Oop, I kind of did the wrong thing. Put my x in the wrong spot down here, guys. It's supposed to be a positive in for x and then a squared. So if I take any positive number and square it, that's a positive. Times 2, that's going to be a positive. So that gives us a negative number. Now, what that tells us is as x approaches infinity, we're kind of doing the sign test, our whole value is going to approach negative infinity. So if the numerator is dominant, just plug in a positive or negative value and see what you get. If it's negative, we're going to go to negative infinity. If it's positive, we're going to go to positive infinity. So one thing I should annotate here is that we're probably going to have answers of infinity or negative infinity. And we just want to know which one by plugging in a positive or negative value. Positive because we're talking about positive infinity here. Okay, let's talk about if the numerator is dominant. If the numerator is dominant, or denominator is dominant, let's see. We have a dominant denominator here, right? 4x squared over 2 to the x. This one is dominant. If the denominator is dominant, then we have a horizontal asymptote at y equals 0. So this entire thing would then be equal to 0. That one was pretty easy. So if you notice that you have a dominant term in that denominator, you can pretty much always just say, hey, it's going to be 0. Now there are some like really special cases that we'd have to be careful of, but really this is going to be true as long as we follow these rules. So why don't you go through and try to attempt those exit tickets and those problems in the Desmos, and I'll see you back in class.